Yeah. Okay, good morning. Can anyone hear my voice?
ครับได้ยินครับอาจารย์
Okay, thanks. Okay, let us start. Actually, this is chapter 7, the general force vibration. It's gonna be the last chapter that I plan to discuss with all of you. However, before we go into the detail of the chapters, let us discuss about the exam. I'm talking about the midterm exam where we test you on the first part of the subject. And I expect to complete my discussion by next Wednesday, Tuesday, maybe. Let me check. Okay. How about this? If I plan to have the exam, maybe using the Zoom, you do the exam like this before, right? Just turn on your camera and we will record during the test. And it take around 3 hours for the test. If I plan to have the exam on the Thursday morning, on the March of 3rd, right? 3rd of March, is cause any problem to all of you? If I plan to have an exam, midterm exam, let me tell you this. I'm sorry. In the morning, let's say start from 9 a.m. to 12. Is that fine for all of you? If any of you have something to do, like you have a class in the morning, is that you can turn on your microphones and let me know if there has any problem. ครับ
class อาจารย์
You have another class in the morning.
maybe started class.
I see. How about in the afternoon? But not on Thursday. Thursday I have a class, so it's gonna be someday weekdays in the afternoon. Like how about Friday afternoon on the 4th of March?
I have a class.
You have a class. Friday morning?
Friday morning I have a class also ครับ
You have a class. How about Wednesday afternoon? Wednesday is on the 2nd of March, right? In the afternoon. Let's say from 1 p.m. to 4 p.m. like this. Is this okay for all of you? No objection, right? Okay, good. So let me have the exam on the 2nd of March in the afternoon. And I think this is on Wednesday. We got one newcomer, not so sure. So may I repeat? If I have the midterm exam on the Wednesday of March 2nd, afternoon from 1 p.m. till 4 p.m. So nobody have objection, right? So you can prepare yourself for the time that we requesting for the exam on that day. Okay, good. So let me fix the date for that. The exam, midterm exam. And in the exam is a kind of the open books. So you can expect that any type of the textbooks, lecture note, any information and documents are all allowed for you for the test. And we will discuss again about the previous exam and the exam they're gonna have for this year with you maybe next week, next Tuesday, I think, before we can complete all the discussion with you. Okay, so let us start on chapter 7. The chapter 7 is a chapter that try to bring you to the more general case in which the external force, the loading that acting on the synchro degree of freedom system has been considered as the general force, any arbitrary force. There's a FT. And this external force FT, previously we considered the case like if the external force is zero, that is a free vibration case in the chapter 3 maybe. And then we move on to the case where the force vibration is considered. And we start with a very simple external force function. This is called the harmonic force function. That is a chapter 4. Then we extend the knowledge of the harmonic force vibration to the case where the force is more general. This is called the periodic force function. Okay, using the knowledge of the harmonic force vibration, we can solve the periodic force function, employing or adopting the concept of a Fourier series as well as the superposition. Then we consider the system again where there is no external force actually, but instead we do have the motion of the support where this fixed support is not fixed any longer. It keeps moving with time. And we found some applications on such kind of situation for the earthquake excitation, for example, or the cloud-induced vibrations, support-induced vibrations. We found a lot in industrial applications, not only the civil engineering applications. Then we move to this chapter, chapter number 7. The force, external force, now it's not any function that we familiar before. You cannot describe by the harmonic function, you cannot describe by the periodic function, and you cannot describe by the any mathematical functions. It's more or less arbitrary. Any any force function you can think about. In this case, engineers look at the problems like this and found that there's a lot of application actually, like the wind, like the earthquake, like a traffic induced vibrations case, like a train induced vibrations, or even the pedestrian induced vibration when the people walking on the bridge. We found that the actual loading to the civil engineering structures, more or less, they are quite random, quite arbitrary, in which any mathematical functions cannot be used to describe such loading functions accurately. So we turn our interest how to get the solution if the force is very general. The idea, like the one that we will discuss today, is the idea of engineer, or maybe I don't know, Duhamel is gonna be a kind of a scientific. He's a scientist in the year, maybe you're talking about almost 100 years, maybe 70 years or something like this, where the man named Duhamel, he proposed the idea like this. Well, the way that the engineer or the scientist try to get the solution where the system or the mass subject to the external force, and this mass is exhibits like the dynamic system, they found that one of the ideas to get the solution is to use a superposition technique that we will explain to you. The superposition techniques here mean the way that the engineer tried to decompose the external force by considering each impulse. Previously on chapter 5, maybe, when we're talking about the periodic force function, the idea is quite similar. But on that chapter, we decomposed the periodic force function by using the summation of many sine and cosine functions. We call that the Fourier series. But on this chapter 7, we don't decompose the force into that summation of sine and cosine. Instead, we will look at the force function directly, piecewisely. Some people call this one is the idea of digitization of force function in the time domain. And they explain that the decomposition on the chapter 5 is the idea of the decomposition using the frequency domain. That's why you can be seen in the sine and cosine term, you see, in the Fourier series. They will keep changing the frequency, right? From omega number 1 to omega number 2, number 3, number 4. Depend on the number of the sine and cosine term that you want to include or taking into account in your considerations, that compose of many frequency. That's why they call the frequency decomposition using the Fourier series. But chapter 7 We never do that. We do decompose the force in the time domain directly. We look at the force function in each time step, time instant, and get the solution of our system due to the impact, due to the effect of each time step. One by one, piece by piece, and superposition or summation or integration there to get the total solution. Okay, this is the background or the concept or the main idea for the chapter 7, which quite different from the idea of chapter 5. We call this a time domain decomposition. Okay, let's see. The idea of the time domain decomposition in this case is look like the one that we put on for you in this figure. Look at the force function F. Assume that you have arbitrary force function like this. And we will try to digitize the force into a many force that acting on your structures. In the figure, you can see that we digitize the force in the small time interval, the tau. At the time t equal to tau, any time tau, let's have the time interval, very small time interval, the tau. And at that time interval, your force function is the function of F of tau, right? This is what is written here. At the very small d tau, you get the order of force is about the F of tau. And we try to get the solution. We want to get the effect of this amount of force, F tau, that will produce or induce any response of the system. To do so, we start with a very simple momentum equations. I think you know about the rate of change of the momentum, right? It's called the impulse. Look at this, the impulse in the time at tau. You can have the general equations for this impulse as the rate of change of the momentum equal to external force. This is very general physics equation first. Okay, this is a change of the momentum. If you introduce the parameters that involve, I have to change the f of time t to f of time tau. And the wording of the dt, you can replace by the d tau. And that's why you can know the change of the momentum gonna be equal to the f tau multiplied with the d tau as in equation number 62. And since the mass of the system is fixed, is constant, so you can have the equation number 63 as the change of the velocity, dx dot, equal to f tau d tau over mass m. Okay, this is well described by the 63. Now on 63, that is telling us This equation physically can be interpreted as when the system subject to the impulse F tau acting on them, the effect of that impulse will create the change of the velocity. If your system is start from zero, velocity is zero. After I apply the force of tau to you in a very short time duration, the tau, I can expect that your system will have the effect of this impulse will create the initial velocity of the mass. And this initial velocity, after I apply the impulse to you or I apply the force F tau on your system, your mass will have the velocity of dx dot. If you start from the initial velocity of zero, you got this as your new initial velocity after the application of the force F tau. Okay? So it looks like you knock on something, like you have the mass on your table and you push your finger to apply the force, or you knock on the mass directly. That amount of the effect of your knocking force, it looks like you put the impact on the mass. It will generate the initial velocity to your mass. And that initial velocity can be described by equation number 63. It depends on the amount of force that you apply or you knock on the mass. It depends on the time durations that you apply this impact force or the impulse over the mass. Okay, so this is 63. From 63, after we know that the effect of the impulse or the force F tau will generate the initial or the velocity of the mass, one can get the response or estimate the response of the system after the force, after the application of the force. It looks like this. At the time tau, of course, you apply the force. Let me draw you again on the same axis. Maybe I put the same axis as the time t, but let I draw you with the green color. The black color is a force, but the green color could be the x, okay? It looks like this. Before I apply the force F tau, is nothing, right? So the vibration is zero. Assume there's no effect of the force in our analysis. But at the time tau, you apply the force F tau knock on me, on the mass. So this will create the initial velocity. So I know that the slope could be something like a positive number if the force is a positive direction. Okay, so the effect of this F tau will create the initial velocity, and that initial velocity will make me to move like this. Okay, for sure. The slope here, that I try to use, the slope here it's gonna be a rectangular, okay, is, let me draw, slope is the x dot zero. okay, is the initial velocity. And it's not zero, right? It has some amount of quantity. In this case, going to be the positive number since the force is a positive direction. And after you have the initial velocity, the system will go free vibrations. Because after I finish the application of the force F tau, we assume there's no external force at all. Only the effect of the force F tau is considered. Okay, assume there's no force before and after. Only the F tau is exit, and we consider only the effect of this. We got the response as the green color. We got the response from the free vibrations due to these initial conditions that induced by the impulse F tau. To get the solution of this free vibration, I think it's better to look at chapter 3, right? Where you can have the, let me turn on the chapter 3 for you. Okay, in chapter 3, when we consider the free vibrations, if my system is the, okay, this one maybe, this, okay. If I look at equation number 16, remember this is a chapter 3, the case of free vibrations. We are considering the case under the impact or impulse of the force F tau that induce or create the initial velocity. And then you can assume that in this case, x0 is 0, but your initial velocity, x dot 0, is equal to what? Equal to, let me draw you again. Where's it? Equal to this amount, right? From 63, F tau over M d tau. Let's go to F tau over M d tau, like this. So in this case, I think the phase angle V, if you introduce to equation number 17, it got 0, right? Since your x is 0. And the thing that happened to the big X is gonna be 0 there, it should be 0 there, like this. So your amplitude, the big XH here is gonna be something like x dot 0 over omega d, right? Okay, so your response x of time t in this case is gonna be something like the x dot 0. It's a f of tau over m omega d e to the power minus cosine omega t and sine omega dt. That's it. Okay, you should obtain this amount of the response x, and this x is explains something that the effect of the force at time tau will create the vibration at any time t, like this. If the tau is fixed at 0, it's easy like this. But now remember, your system is not easy like that. Because that the force you apply is not at time t0, but it's at time tau. 0 is here, right? And I would like to get any response of x at any time t. That's why you should do some manipulations about the t and tau. And you get something like at any time t minus tau, like this, as in equation number 64. Remember, since the effect of this force is not the whole history of the force yet, it's just the one piece of the force F tau. And actually the force is the clean function, right? You have many force, and at any time there is a force. Let me do it with the another color. It's better. The clean is a displacement, right? Let me try to draw you with a blue color, like this. You have a force all the times, but at any time tau, we consider the response and the effect of the force F tau only. Therefore, when I write down the response x, I would say this is only the variation of x. Okay, variation of x due to the force F tau. I'm not saying this is the whole effect of the force. It's only the effect of the force F tau will change the displacement function of mine as in equation number 64 as the variation of x of time t, like this. Okay, so if you want me to combine all the effect of the force that acting on the mass before the time F tau, of them all together, then I need the summation. I need to summation or combine the effect of every piece of force that acting on my mass, starting from time equal to 0 to any time t that you're asking for. That's why from 64, the total response that combine all the effects of every piece of force from time 0 to any time t, we given by 65. Okay, by performing the integration of 64 actually. You can combine all of them. Put the integration, all the effect of this 64 from time 0 to any time t. That's why you see the integration starting from 0 till t, time t. I have to combine or integrate all of these effects to estimate the response of x at time t. Of course, the effect of the force in the future at the time t plus delta t or t plus some number have no effect on my response at time t, right? I cannot taking care about the future force because the future effect of the force, I mean the future force, the force at the in the future. For example, if I consider the effect until here at time t, the effect of the force here, the effect of the force there have 0 on me. You cannot, or it's impossible to say that the future force, the force in the future will induce some vibration on you in the past. It's impossible, right? Therefore, why the integration, if you take, I'm sorry, from 0 till until at the time t, like this. And this 65 has a very, very big name is known as the convolution integrations. And some people call following by the name of the man who proposed is the Duhamel integral. So this is a kind of a special type of the integration where you see you have the integration, not dt, but it's d tau from 0 to time t to obtain the xt is called convolution because the effect of the past will keep on the present or the response you obtain. They combine all the effect of the force in the time domain, how to say, style, not the frequency domain. Okay. Let's look at the explanation a little bit to make it more clear to all of you. The force F will then decompose into many piecewise along the time axis in the time domain, in other words. For example, at time t0, we consider the first law at time t0. Assume there is no force yet. So at this time instant, the force is not applied yet to your building or to your structure. However, it's possible that your structure or your system could have your own initial displacement or initial velocity. Because this one is an initial condition, right? Assume you have some initial conditions. And that's why you see in the impulse response, you could have the pink color, right? The initial displacement like this. Okay? And if I let these initial conditions to create the response of the system, we call this as a free vibrations under the initial conditions like this, and they call it the R0. Okay? And the next step, at time delta t, the external forces come to us and it's called F number 1. This is the F tau and tau equal to 1. For very small delta t. And the effect of this Ft, you know, this creates the x dot 0 of number 1, right? The effect of this impulse from 63, we create the initial velocity. And that initial velocity is the slope here. And the slope here, we think is equal to that amount of x dot 0, number 1, step 1. And once you apply, and the initial velocity, the initial displacement here is 0, exactly 0. X0 at the step 1 is 0. This is a given initial conditions due to the F number 1. From 63, right? We know this. And then it's induced to vibration as in R1. And you see, it's R number 1 is the red color, show you the response. This is the free vibrations again. Then we consider the next step at the time t equal to 2 delta t. At the time t equal to 2 delta t, now is a tau equal to 2 delta t. You can imagine you have F number 2 like this, right? And the effect of this F number 2 will create the initial velocity of the step 2. And see the effects of the, let me draw you a little bit. the effect of the forced tau, we cannot create any past vibration, okay? So that's why from 0 to 2 delta t, you can have the 0 response, R2. But after you apply the force F2, you can have the initial velocity. And this initial velocity is x dot 0 number 2. Okay. And of course, x0 of step number 2 is 0. That's why you can draw the R2 like that. The response of the step 2 is this one. This is, we are talking about this curve is x of time t, right? This is a free vibration like this. Okay, I hope you can imagine that for at the time tau equal to n delta t, you can have the f n like this. And if the force is like that, your slope here is going to be a negative initial velocity like this, right? So it's x0 step n like this. And at the time from 0 to n delta t, you can expect the response to be exactly 0 because the Fn cannot create any vibration in the past. It's only be able to create the vibration of my system from time equal to n delta t and then after only. Okay. So now you can see all the effect of each impulse of F1, F2, F3, F4 until Fn. The idea like this will be, you can combine all the effect of this impulse response all together. You sum them up and draw what they call the total response. For example, if I say this is a total response, at the time 0, the total response gonna be the effect of the first piecewise only at the or initial conditions only. That's why you can have the R0, sorry, to control your total response. But at the time t equal to delta t, you see the effect of your total response gonna be the summation of the R0 plus R1. That's why they create the curve like that for you. And the next step, the effect will include the R number 2, and the next step will include the R number 3, something like this, right? You sum it up and you accumulate the effect of each piecewise one by one, and then you obtain the total response at any time, like this. Of course, the idea like this is quite understandable, and it's quite okay, easy, maybe not so difficult to understand, but it's maybe quite difficult to implement it, to implement in the real situation where you need, I don't know, in the many years ago, we don't have a powerful computer. So it's very hard for our civil engineers to taking care of big problems where you have a lot of degree of freedoms and forces. But nowadays, it's a simple worksheet. You can think about the Excel, right? You can use the Excel like that, what they call the worksheet or the macro, so that you can do the manipulation like this. Easy. It's not so difficult now today. And if you dream about, you write down your own programs, mathematical programs, no matter you use MATLAB or you use the Python to write down the way of the Duhamel or the convolution they propose. It's not so difficult to get the solution, I believe. However, I think the convolutions is not as good as the other techniques that you will learn and discuss with Dr. Chatpan in the second part of this subject, where maybe he will introduce you the idea like a direct integrations of the equations of motions and using what they call the Wilson-Zeta method or whatever we can think about. There's a lot of techniques using the direct integrations. And that can do quite efficient using the numerical, using the software of the new computers. It's better than the convolution. I mean, in terms of accuracy you obtain, and in terms of the how do you say, the computation efficiency, where you can wait just a few seconds and you obtain the response of the system, the dynamic system, even though it's a tall buildings or the long span bridges. But using the Duhamel or the convolution, as I discussed with you today, it takes a lot of time. The computation efficiency is not so high as comparing with the direct integrations. So I think maybe later on, I will discuss a bit with one of the technique, not the direct integration, not the convolution as shown you today, but is the extension of the state space technique that I think all of you have studied with me about the applied mathematics, right? And that technique has, I think, is faster, is more efficient than the direct integrations. And I'm not so sure that Dr. Chatpan will discuss about that technique with you, because it's not in a standard textbook about the dynamics of the structure that he used as a reference. Therefore, I plan to discuss with you maybe next Tuesday about that technique, and that is very helpful, at least for me, when I do the research. I often use the state space, and by using the MATLAB, it's very easy and very simple. I will show you about that later. Okay, this is just one of the example. Is the way we apply the Duhamel or the convolution integrations. This example, I think, is the case where you have a single degree freedom system and subject to the force like this. Very simple case. Let me draw you the blue color. Because if the force function is very complicated, it's very hard to perform the convolution. It's very, very difficult. Since you need the integration by part, this is a case where only the spring is introduced to the system and is subject to the external force like this, Ft. And this force Ft, even though it's say as the constant function, but in fact it's like this. Let me draw you with red color. Before time 0 is 0, and when time equal to 0 is go to this amount, go to F0, and it's kept constant forever. Like this. Just this, what they call this is step function. This step function, force function, if it's applied to the system like a mass spring system without any damping, okay? The damping is zero, it's assumed zero here. The reason is if you contain the damping, the integrand inside the integrations, it become more complicated and it's very difficult to get the solution accurately. So that's why we assume the damping is zero here. The equation 65 will apply now. And the F tau can be fixed as the F0, okay? And you just perform the integration inside. So you see, you can remove F tau. It's very difficult if your F tau is changed with the time t or with the time tau, but this example is easy, right? Because it's become the constant F0. So you just remove this F tau out from these integrations. So that's why you got in the second equations is equal to F0 over M omega. Okay. When the damping is zero, you have only one omega, okay? You don't have omega and omega D. The omega D and omega are the same, is the omega now, because the damping is zero. That's why you see you obtain on the second equations, the integration from 0 to t of the psi omega t minus tau d tau. And this will create for you, the result is like this. It's the x0 1 minus cosine omega t. And if you plot this one, I think it's like this. This is the force that I explained to you is something like this, right? It's step force function. Before is zero and step like this forever. The xt is the response. And the response here show you that the amplitude is equal to the maximum of the +2 and -2, right? It's gonna be +2 when you got cosine omega t equal to -1. And if your cosine omega t is the +1, I'm sorry, -2, you cannot have this. Got +2 and 0, right? When cosine equal to 1, you obtain the minimum, that is 0, exactly 0. And when cosine omega t equal to -1, you get a +2 as the total response x, something like this. 2 of x0. That's why you can expect the curve like that. See, if we treat this force as a static force, I just apply the force and keep it static, right? It's constant. Some people might feel this is static case. You apply the constant force, but in fact, it's not. If your system is a dynamic system, you're gonna have the vibrations like this. And the response, the maximum response is 2 times comparing with the static response. The static response is very simple to compute, right? It's your x0 is equal to f0 over k. But now here, this is 2 times of the x0. This is my x0. This is your x0, okay? Equal to 1. So the response plotting of this is plotting the ratio of x of time t over x0 for you. That's why I got from 0 to 2 as a maximum. That's it. Okay, let me think about this. If the force function is not the step force function, is is any type of a function. For example, imagine if your function is just a linear function like this. I have high the force and increase the force with time like this. The F tau here is gonna be something like any function like this, right? If the blue color is gonna be something like a tau, something like this. A constant multiply with the tau function, with the tau parameters. And you see, you have the tau psi omega t minus tau, e to the power something t minus tau. Just make the thing more and more complicated, right? If you have the damping as well, and the damping is not 0. I myself cannot imagine that I have ability to perform the integration, the complicated function like this. Maybe some of you might keen to do so, but I'm slender. I found myself it's very hard. It's not easy, mathematics. It become a complicated function, complicated integration for me already. That's why you see the idea of the Duhamel or the convolution is not so good to perform for the application of any closed form or analytical solution. To obtain analytical solution is not so easy. More or less is often apply for the numerical techniques. So when the people use convolution or the people use the Duhamel, they're thinking about the numerical techniques. They don't believe that they can apply directly for any type of the function except the constant function like the epsilon, like this, like the example we show you. And especially the case where you have the damping, right? The term become more and more complicated. So instead of using the thing like the example show like this, we engineer often apply the Duhamel for the numerical techniques. Unfortunately, I don't show you the numerical techniques or numerical example of the Duhamel. You can find the example of the Duhamel or the convolution integrations in many standard textbooks. But believe me, it's not so interesting to all of you based on the computer technology we have in hand today. A better way of a numerical technique is not Duhamel. You may think about the direct integrations that Dr. Chatpan will discuss with you on the second part. Or you may think about the state space technique that I will discuss with you next time. Okay. So the conclusion that I would like to discuss with you for the today's discussion is, when the engineer faced with the problems where the system is subjected to the external force, and that external force is more or less the general force, arbitrary force, we have the technique for them. We have the solution techniques for them. And one of very basic techniques that many standard textbook on the vibrations of the structure mentioned about is about the convolution. And the idea of convolution is very simple to understand. It's a kind of a decomposition using the superposition. You decompose the force in the time domain and compute the total response as the summations of those decomposed piecewise force functions. Using the superposition techniques, one assumes the system is a linear system. Therefore, get the total solution. The kind of using superposition is allowed or is possible. However, idea is very simple. However, when we look at the mathematics, we found to obtain the total solution based on the concept like this, it's not easy. At the end, we found mathematics of the convolutions. That means the engineer who applied this concept or this idea have to involve with solving the system using the convolution integrations. And that convolution integrations is not so practical in terms of the computer efficiency. It's better to using another techniques or another algorithms to solve the system under this general force. However, we learned this chapter just to show you that the background or the idea of piecewise decomposition is possible because it's very natural and very straightforward to have the idea like this. Okay, so we just prove to you and let you know about the very basic technique that many engineers know, even though it's not efficient for the today computer computations. Okay, this is my last chapter on 7. And I hope since we already fixed the exam date on early next month, so you have only 2 weeks from now to prepare yourself for the exam. I think maybe we don't need to have a Zoom meeting on this coming Thursday so that you can have some time review the chapter 1 to chapter 7 and let me know your questions that we will plan to have a discussion on next week, Tuesday. Okay, on next week, Tuesday, I plan to come to meet you and discuss about the, of course, the previous exam and the numerical technique using this state space that I mentioned. I will show you, I will use the MATLAB to solve maybe a multi-degree freedom system, maybe a very simple 2-degree freedom system, maybe. To show you it's very fast, even though the input is a ground motion, the earthquake or the sine function, cosine function, every function is very simple. Okay, so if you have any questions so far, this is the time. Any questions from you?
Ajahn?
Yeah.
The exam gonna be online on site, Ajahn?
I have fled. If actually I can do the exam on site as well if you request for, but I don't know, maybe one of you is not comfortable or maybe have difficulty to come to university next month. Let's talk about it. Anybody has the problems to go to university? to have the exam, or you prefer to make it online? Let me have your idea about that, because I happy both of them. No matter you want me to go with you to university to have the exam together, or we just turn on the computer and camera and do the exam at home. Which one you like? No idea? Very quiet. It means that you prefer the online exam. No. Okay, I very quiet, right? So, okay, just have the online exam like this, I think. I afraid maybe some of you hesitate to say that they maybe only stay outside Bangkok, very far away, right? Maybe at their hometown, and they don't want to come to Bangkok just for the exam and then return back their hometown, I think. Any other questions? Okay, if you don't have any questions, we have the live group and keep watching the group, and it seems there's no question yet. But I expect when I already fixed the exam date and it's quite early compared with other subjects, I believe that maybe some of you start to reading the books and solve some the example, and you find some difficulty and maybe the questions, and keep using the live group to post your questions. I try to respond of yours, and hopefully on next Tuesday, I will come to meet you again. And if you have a lot of questions, we can have like the next Thursday meeting, because we have plenty of time right before the exam. So it's up to you if you want me to meet you to discuss with you again about some of the questions you might have. Well, once you don't have any questions for today, I would like to stop my discussion here. And remember, we don't have a class or the meeting, Zoom meeting on this coming Thursday. Let you study and review the chapters, all the chapters, because we already end the discussion. And collect and keep your questions for the discussion on next Tuesday, so that we can finish everything, including explain you and answer you and discuss with you all the questions you might have. Okay, so I stop here and hope you have a good day, and goodbye for you.
Thank you.
Thank you. Welcome.
อาจารย์
Yeah, good day. Bye.
Goodbye อาจารย์
Bye ครับ